Okay, so the quiz is to graph this function as we did in class last. Now, you haven't had an assignment on this, so you haven't necessarily practiced this. We're just trying to refresh it. Okay? And everybody did quite well. I gave you the hint, find the intercepts, and everybody, okay, you find the intercepts. Now, I keep urging you to write out what you're doing and why you're doing it. Otherwise, you're just memorizing a bunch of steps and you don't know why you're doing, so you don't remember them as well. Take the time to write them out. Okay. To intercept y equals 0. Well, y equals f of x equals x squared plus x minus 6. So x squared plus x minus 6 equals y. If y equals 0, that gives us x squared plus x minus 6 equals 0. Okay? When you do a problem like this, you ought to write out what you're doing and why you're doing it. Okay? To the extent that you understand it. Sometimes you're just imitating a step. You write out, dang, I don't know why I do this, but I know I've got to do it. Okay? Because that's what the examples do. That's okay. You want to try to get beyond that point. But it's valid to do it. Everybody's going to have to do that once in a while. So we have this. This is quadratic equation. Okay, one way or another. Reinforce the fact you got a quadratic equation. You could just put like or no, that's a quadratic equation. Just to remind yourself that that's something you need to look for. Okay, so it's a quadratic equation. X equals -1 plus or minus square root of 1 squared minus 4 times 1 times 6 over 2. And of course, if you don't remember the quadratic formula, you should write it out and write out that A equals 1 and B equals 1 and C equals -6. But everybody here understands that quite well. But again, write out the detail and you'll remember them much better. Well, that's going to be -1 plus or minus the square root of 25 over 2. So then you get your solution. It could be 2 or -3. Now I'm assuming you know how to do a quadratic equation. If you're watching this video and don't know, go back and review it because had an assignment on the quadratic formula, it should be pretty automatic to use it. Okay. At this point, that's something to put on the graph, which would be 2 intercepts, 2x intercepts, -3, 0, and -2, 0. Okay. Now, y-intercept x equals 0. So y equals x squared plus x minus 1 minus 6, sorry, equals 0 squared plus 0 minus 6. And of course, that comes out -6. So the y-intercept is 0, -6. Could include down here the step where we identify that when x is 2, how did x end up as 2? We started with y equals 0, right? But when x is 2, y is 0, so the x-intercepts two, 0, and 0, -3. We should take the time to do that. You can see what I did there? First place, I didn't put a comma in there. Second place, -2, 0, 2, 0, -3, 0. And of course, those are the points that I graphed. Now, here we have the y-intercept, which we found to be 0, -6. So we'll put that down here. Then the axis of symmetry. Two ways to get it. It's halfway between 2 and -3. So you can just add 2 and -3 and divide by 2 and get -1/2. But I'm going to emphasize just in case you forget to do that or want to double check it. And where do you see the axis of symmetry? Well, you know because you did it. Okay, you know because you did it that you can just add these and divide by 2 because the axis of symmetry has to be halfway here, otherwise this thing wouldn't be symmetric. And we know darn well that it is. Well, right here is your axis of symmetry. -b over 2a. Okay, why is that? Well, it's because these are your two zeros. Plus and minus gives you the two zeros, right? Well, what's halfway between -b plus the square root and -b minus the square root? It's -b. So this has to be halfway between the two zeros. Okay. So that I'll use a little notation. I'll put an abbreviation of symmetry. X symmetry is -b over 2a, which is -1 over 2 times 1, which is -1/2. Easier, of course, just to add those and divide by 2. But either way, we get the axis of symmetry. And you identified, you abbreviated that ALS, which is fine. Okay, you knew what it was, you labeled it, very good. And then the vertex. Is on the axis of symmetry. So x equals -1/2. Y equals x squared plus x minus 6 equals 1/2, sorry, negative 1/2. 1/2 minus 6, which equals 1/4 plus 1/2 minus 6. And we can do the fractions. We can say that's 1/4 plus 2/4 minus 24/4. Okay, and now it's easy to add. That gives us 1 and 2 is 3 minus 24 negative 29/4. And well, I'm gonna write it again. X should be negative 1/2. Okay, now I think somebody in the class made that mistake. I'm gonna blame. No, I'll take credit for it. I did it too, and I didn't do it intentionally. But if it makes you feel better, I did it. And what you did was you recognized that what you got didn't make any sense. Okay, because the axis of symmetry has to be lower than the y-intercept, because you know what the shape is going to be. Okay, the vertex is going to be here, and it has to be lower than this. And what you got wasn't going to be lower. So let's write it out again. Okay. And now we can write it as 1/4 minus 2/4 minus 24/4. And that's going to equal negative 25/4, which is negative 6 1/4. Now I emphasize again that the first place it would be good if I did this, where you could see it. So again, finding the vertex, it's on the axis of symmetry, so x is negative 1/2. There's your axis of symmetry. So we just plug negative 1/2 in, do the fractions, and we get the result. It's important to do the fraction. That's going to come up in rational functions where you have to do it with symbols. You have to add things and multiply things. So you have to know the rules for multiplying and adding fractions and dividing fractions. Okay. In any case, it tells us that our vertex is just a little lower. So now we sketch nice symmetric graph that almost goes to the right point. Okay. Okay. Now, I think we did this last time, but if you have a quadratic function, what if you have this? How do you graph that? Well, you could use the method that we just did with a quadratic formula and all that stuff. Find the vertex, the intercepts, and all that stuff. You can find the intercepts as far as that goes. Okay. And open math is probably going to advise you to do that. But the one thing I'm going to want to see you be able to do is understand that this is the toolkit squaring function. And it's shifted 4 units in the horizontal direction, 6 units in the vertical direction. So it's just a transformed squaring function. Now, before I forget to do it and run off the board again, let me just jog the camera a little bit. Okay. So it's fairly easy to see where this is. We'll have our toolkit squaring function here. And we have a scale. So we're not going to be real specific here, just indicate at x equals 4, y equals 6, we got a vertex. Okay. And the graph is going to look just like this one. Since we don't have a vertical stretch, it's going to be like this. Okay. Now we know, first place in my class, we do this in a box with a red, within a rectangle, using a red dot at the vertex. Okay. And if you're in my class, you know how to do that. If you're in another class, you can say, okay, well, let's see. There's x equals 4. So here's x equals 2. And we know at x equals 2 that y equals 4. So we know we have the point 2, 4 on the toolkit function. That means if we go over 2 units and up 4 units on this graph, go over 2 units and up 4 units from this vertex, we're going to get a point on this graph. Now, I just want to kind of give you that picture. I think everybody here knows how to do those details. Let's see what this function looks like if we expand it, meaning we do the square here. Now, 2/3 of the people in a pre-calculus class come to class thinking that if you square x minus 4, you get x squared minus 4 squared. And that's absolutely not true. What you get when you square x minus 4 is what you get when you multiply x minus 4 times x minus 4. And that is first of all, it's x times x minus 4 minus 4 times x minus 4. That's familiar? That makes sense? It should. It's very important. And then that equals x times x minus x times 4. And I'll write that as 4 times x. Okay. And then it's minus 4 times x minus 4 times minus 4. And then there's our plus 6. this comes out then, x squared. We have minus 4x and minus 4x gives us minus 8x. Minus 4 times minus 4 gives us plus 16. And finally, this equals x squared minus 8x plus 22. Okay? So please don't make the mistake of thinking that x minus 4 squared is x squared minus 4 squared. Distributive law has to be true. And we're going to have to use a distributive law to multiply that. Now, there is a special product. You know, the quantity a plus b squared is a squared plus 2ab plus b squared. But I'm going to want to see the distributive law because experience is that people don't remember formula. Okay. Okay, so now how would we graph? X squared minus 8x plus 22. Find the x-intercept. X-intercept 0. So x squared minus 8x plus 22 equals 0. Now I'm going to put some dots down here, and I'm just going to write out what happens when you use the quadratic formula and do some simplification, which means I'll probably make a mistake, but you're going to get x equals 8. It's going to be minus b minus negative 8 is going to give you 8, plus or minus the square root of what? 8 squared is 64. 4 times 1 times 22 is 88. 64 minus 88 is negative 22. Negative 24, sorry. Now, if you do the quadratic formula, do it correctly and carefully, which I know you can do, you're going to get this. We got a square root of negative 24. It's not a real number. That's an imaginary number. What does that mean? Okay, well, this graph, it's not going to have x-intercepts. Now, if you've done it already in that form, you see that this graph isn't going to have any x-intercepts. The vertex is above the x-axis and the graph opens upward, so it's not going to intersect the x-axis. So we don't have our x-intercepts. And that, in some sense, can make it a little harder to graph. We still know the axis of symmetry. Right there. Now, I'll write out x equals negative b over 2a. But you don't want to memorize that as a separate formula. You will have to memorize a quadratic formula, okay? You realize that in the quadratic formula, the 8 is your negative b, and the 2 is your 2a, right? So we have negative b over 2a right there. And what we did with the quadratic formula, there's negative b over 2a. Okay? If you know the quadratic formula, you identify that, which is then negative of Okay. Over 2 times 1, which is 4. So now we can do some graphing. Axis of symmetry is at x equals -4. Not -4, it's 4. Okay. Now, we already saw that because this function is the same as this one, just in a different form. But where's the axis of symmetry in this one? It's x equals 4, right? We did that when we did it by transformations. So there's the axis of symmetry. Y-intercept I wrote that real small because it's really easy to do. We put in x equals 0, that's where the y-intercept occurs. We see it's at y equals 22. So we'll extend this axis a little bit and say that, okay, y equals 22 is going to be up here. And there's our y-intercept. We have the axis of symmetry and we have the y-intercept, and we're going to be able to figure out the vertex. On the axis of symmetry, so x equals 4. Thus, y equals 4 squared minus 8 times 4 plus 22. That's going to come out 16 minus 36 plus 22, and that's 6. So if y equals 22 here, 6 is going to be down here someplace. Okay, so here's our vertex. The 4, 6. Now we've already graphed the thing in this form. And we see that the vertex is at x equals 4, y equals 6. So now we have these 2 points. We know this is the low point, and we can sketch a graph. Now we can sketch it down to here, but we know it's symmetric, so it's just going to be reflection when we go up here. There's our graph. Okay. So we have 2 ways of graphing one of these things. One by transformations, and one by finding intercepts and axis of symmetry and vertex. Okay. If we don't have the x-intercepts, we absolutely need to find that vertex. And even if we do have the x-intercepts, the vertex is maybe the most important point. So we want to find the vertex. And that's it. That's what you need to know about quadratic functions. Okay. Okay, our quiz main question was graph this function. And what do we do? I'm going to go into a little more detail than what your homework did, because I'm trying to anticipate a lot of stuff in chapter 3. Okay. So first of all, what's the degree? Degree is 3. Why? Because we multiply this out, we're gonna get x cubed plus a bunch of other terms. What does the degree have to do with it? Well, it tells you what the long run behavior is. Okay, so long run. Long run is that of x cubed. And the x cubed graph, you know, from having constructed it, looks like this. Okay. So as x goes to infinity, p of x goes to infinity. X goes to negative infinity. To negative infinity. Now you can think about that just with numbers. I mean, you know that 1 cubed is 1, 2 cubed is 8, because if you graph the toolkit cubing function, which you have to know, okay, you're going to get the points 1, 1, 2, 8. Okay. You're also going to get 1/2, 1/8. Now, open math really does something very bad. At least one of the things, one of the videos from open math tells you that the cubing function has a graph that looks like this. Okay. It absolutely does not. It flattens out. And I can't believe somebody actually did that. But then I can't believe some of the things I actually do. No stones being thrown here. Sometimes your brain just doesn't engage and you do something really stupid. I do it at least once a day. Of course, they have the opportunity to edit their videos. I do something stupid, it's there for posterity. Okay? Because I can't possibly edit all these videos. Okay. This takes way too long. So anyhow, yeah, well, it doesn't look like this around the org. It looks flat around the org. And that goes with the way I showed you last time to construct the x cubed graph. Okay, using a whole lot of lines. So subdivide. And it keeps subdividing for a long time. And the point you get here is so close to the x-axis, you can't even distinguish it. Same thing over here. Then the next point's like here, and the next point's like here. And the graph is going to be like this and like this. And if you do what I said, you see that it's going to be very flat And the other way you see that it's going to be very flat is you can make a table. Now, I think that for some inexplicable reason, somebody in one of the open math videos did this thing without cubing 1/2. And that's how they ended up with this. Okay? You're going to get 0, 1/8, 1, 8. 8 is 8 times 1, right? And 1 is 8 times 1/8, right? So 8 is 64 times as big as 1/8. So this point is 64 times closer to the x-axis than this point. All right. This point is 8 times closer. This point is 64 times closer than this one, 8 times closer than this. So we flatten out. Now that's going to be important. I'll show you why. The sequence of power function. Odd number power functions all look like this. Except the higher the power, the flatter they get down. Because if this is x to the 4th, you'd have 1/16 here and 64 here. If it was x to the 5th, which is your next odd numbered power function, you'd have 1/32 here and 32 here. And this point would be 1,000 times further from the axis than this point. Okay? Now, odd numbered power function, that's x cubed, x to the 5th, x to the 7th, etc. The graph, and I'm just going to do the first quadrant. Graphs might be like this, and then flatter and much steeper. Okay, but they all do this. Well, okay, they all look something like this. They all look a whole lot like the x cubed function, except that they can get very flat. If you take a high enough power, the graph would actually look something like this. It would almost have a sharp corner here. Just be a little rounded here. It would be almost 0 out to here, and then it makes a quick turn and it goes almost vertical. It's not really vertical, but it's really close. So the behavior gets close to something like this almost squared off function. Okay. So if you see a power function that has a leading term that's an odd power, and if it has a positive coefficient, then it's always going to go to infinity on this side and to negative infinity on this side. If it has a negative coefficient, like had a negative in front of an x cubed, well, that would flip the graph this way. Because a negative in front of your function reflects it through the x-axis, right? Multiply by negative. That changes your vertical stretch and all that stuff, right? So that's what's going on. For even powered functions, they all look like parabolas except they get flattened. Okay. Even powered functions have graphs look like parabolas or much flatter. And eventually they get so flat they almost look like this. They've got a positive coefficient. They go to infinity on both sides. They have a negative coefficient. They go to negative infinity on both sides. That's it. That tells you how you get the behavior as x approaches infinity. Now, on your paper, I hope I saw you considering the behavior as x approaches infinity, because that's what's going to be the difference between this function and this function. Okay. Now, all this here is just a discussion of the way the function behaves as x goes to infinity. And I'm just going to erase that part of the board. Yeah, I am recording good. Okay. So let's look at this function, okay? P of x. So right now, we know that P of x goes this way and this way because it acts like x cubed. What I say is what this function looks like, if you zoom back, it just looks like this. But if you zoom in, you see that in the middle here, it's got some little wiggles. Okay, and what you graphed, you didn't graph the big picture, you graphed the little wiggles because that's what's really interesting. Okay, and that's what you've been taught to graph. And you picked that up well. People did very well in the assignment. They came in here pretty much knowing how to graph these things. Maybe left off a detail or two, but on the whole, it looked pretty good, as it usually does. Okay, so zeros of P of x. That is x-intercepts, we call those zeros when we're talking about polynomial. P of x equals 0. So x minus 3 times x plus 5 times x minus 7 equals 0. So that x minus 3 equals 0, or x plus 5 equals 0, or x minus 7 equals 0. Obviously, if x minus 3 is 0, since it's multiplied by everything else, the whole thing is going to be 0, right? Same thing for x plus 5, same thing for x minus 7. If none of these are 0, then they're not going to give you 0, right? So the zeros are exactly the solutions to these three equations. And those equations are easily solved. X equals 3, or x equals negative 5, or x equals 7. Okay. I started to draw it over there, but I better draw it over here. Okay, so again, we have our long run behavior that we've already figured out. We have negative 5, 3, and 7. So negative 5 might be there, 3 might be here, 7 might be here. The y-axis might be here. That makes sense so far? Because that's pretty much what everybody did. So this point would be negative 5, 0. This point would be 3, 0. This point would be 7, 0. At this point, you figure that you better, if you're gonna draw the curve, it's gonna come up from here, it's gonna come down here, it's gonna go up here, right? And have that shape, and that's a shape I saw on almost everybody's graph. But we want to get the y-intercept. That occurs when x equals 0. And I keep preaching, going to say it too often, although it really bears saying quite often. You want to write that down. Okay? X-intercepts occur when px equals 0. We get the y-intercepts occur when x equals 0. So that y equals p of 0 is 0 minus 3 times 0 plus 5 times 0 plus 7, which is equal to negative 105. Uh-oh. No, it's 0 minus 7. If it was negative 105, I'd be in bad shape because I can't come up through here and get back down to negative 105 without going through the x-axis. If I go through the x-axis, then p of x is 0, but it can't be 0 there. It can only be 0 here, here, or here. So we can only go through the x-axis at these 3 points. So now, to fix that, it's positive 105. So I'm going to draw a little line here. Y equals 105. And there's the y-axis. Yep. 0, 105. Okay, now I can go through these points. So I'm going to come up from here. I'm going to go up a little over this point so I get through there smoothly. Then I come down like so and come up. Now, most people are going to make the high point here, but there's no reason that your y-axis should be a peak. Okay, so don't deform the function to go through this at a peak. Goes through the y-axis where it goes through. Okay. When you take calculus, you find there's a very easy way to find what these peaks are, where they are. It's like a vertex here and a vertex here, but those are, we really don't call those vertices. Okay. There's a very easy thing you do. Okay. But so you can exactly locate these points. But you need to use calculus to do it, so we're not going to do that in this point. All right. So there's your graph. Now, what I want to make here is what happens if we do this graph. Okay. Think about it for a minute. What's the long run behavior of this function?